Now the question for us is how can we utilize the efficiency of binary architecture while minimizing their errors? And our answer is calibration. But calibration of binary currents is not trivial. Calibration of unary currents is easier because you have the unary currents and then they're all the same, and then you calibrate them against common reference, and that's it. The challenge in binary converters is that you need to calibrate each binary reference to an exact portion of the reference, to 1/2, 1/4, 1/8, etc., etc., etc. And this is the challenge: how you calibrate the binary currents to an exact portion of the reference. And here is our algorithm, how we do it. So for our algorithm, what you need is two sets of binary currents, or two digital to analog converters, binary digital to analog converters. And then the algorithm is as follows. So here I illustrate this with a scale, but in practice this is done for calibration of current, so we use current comparator. So on one side we have a reference, and on the other side we put the MSB current of the first set, and all the other currents, plus one LSB. In other words, what we have here is all the currents of the first binary DAC cell, and then this is nominally, of course, equal to the reference. However, because of mismatch, the scale, the current comparator will show this branch is higher or smaller. If it's smaller, what you know, if it's lighter, you need to add some current to balance the scale, to balance the current comparator, or subtract current if needed. And this is what you do, and subtracting current from the MSB of the first set, the MSB current of the first set. So you add a little bit current or subtract a little bit current from it through a calibrating DAC until the scale changes its sign. So this is an indication that both inputs of the current comparators are approximately equal to within the quantization error of the calibrating step. If you reach this point, you remove the MSB current from the current comparator and you put in its place the MSB current of the other set, of the other binary DAC. So this is the MSB current of the other set. So this is the same here. O is the same. Of course, now the scale will change. The current comparator will indicate one side to be bigger, and then you compensate again by adding or subtracting a little bit current through a calibrating DAC from the MSB current of the second set until both terms are equal, until the current comparator changes its sign. When you reach this point, what you know is that the MSB current of the first set is exactly equal to the MSB current of the second set within the quantization error of the calibration, within one quantization step of the calibration. And this is because this and this and this and this are the same, so they don't change. In step 3, what you want to do is to not only the MSB of the first set and the MSB of the second set to be equal, but you want their sum to be equal to the reference. So if they are equal between each other and their sum is equal to the reference, this can only mean that each of them is 1/2 of the reference. And this is how you calibrate to an exact portion, in this case 1/2 of the reference. So you connect the MSB of the first set and the MSB of the second thread on one side of the current comparator, and the other side is of course the reference. And then you change the calibration DAC, so you add or subtract current simultaneously of DAC 1 of the MSB of set 1 or set 2. If you change it simultaneously, you still keep both currents the same, but you change only their sum. And when their sum becomes equal to the reference, then each of them is equal to exactly half of the reference. So how to calibrate the next bit, MSB -1, it's illustrated here. The initial steps are the same as before. So on one side of the scale we connect all the currents of the first set, and then on the other side the reference, and we will change only the MSB -1 until the scale changes its sign, until the current comparator changes its sign. When this happens, we will remove MSB -1 of the first set, and at its place we'll connect MSB -1 of the second set, of the second DAC cell. We will perform the calibration until this whole thing is equal to this whole thing, after which we know that this is equal to this, so the MSB -1 from the first set is equal to the MSB -1 from the second set, because this and this are the same. Then in the last step, what we do is that we connect on one side both currents, MSB -1 first set and second set. Normally they should equal to half of the reference. And then here we connect the MSB current of the first set, and here is the reference. Keep in mind that this current, the MSB current, is already calibrated to half the reference. So then if we start changing MSB -1, both currents, in the same way, so that we keep both of them equal to each other, but then we change the sum, when this changes, when the current comparator output changes, this is an indication that the sum of these two currents is equal to the reference minus the MSB current. And the MSB current is already calibrated to half the reference, which means that each of the MSB -1 currents will be exactly equal to 1/4 of the reference, etc., etc. You implement this for all binary currents. So this calibration is a startup calibration, and it's only applied to amplitude errors. So to prove this in practice, we designed a 12-bit segmented 12-bit current steering DAC cell. So for this work we needed 12 bits, high sampling rate of 1 gigasample per second, and the application requirement is that we have to use thick oxide transistors. So, and thick oxide transistors are large transistors, so in this technology they were 280 nanometer. So this does not help with the area, but we had to do. Because we needed high performance, and we cannot calibrate timing errors for binary DACs. We chose some segmentation, so we allowed 4 MSB to be unary and 8 LSB, which is still a large portion, was binary. We calibrate everything, so all the unary and all binary with our algorithm. The reference, of course, is equal to the nominally equal to the unary current, so all the unary currents are calibrated to the reference, and then binary currents follow with the algorithm that I just presented. It had to be also high performance, so we could not use fully binary architectures. Still, we cannot calibrate timing errors, we can calibrate only amplitude errors. So this was the reason why we chose segmentation, which is 4 MSB bits unary and very large portion of binary LSB, 8 LSB binary. And to minimize all the dynamic errors so that we keep good performance, good linearity at high frequency, the most of the switching, digital part, is implemented in a low voltage CMOS logic with thin oxide transistors and also very small area, including the synchronization. And following the requirements of our applications, the output cell DAC stage needs to be in thick oxide transistors. So high voltage CML level shifters need to be used, and of course thick oxide drivers.